Hi, this is Mr. Steele one more time. It's actually like the 17th time that I've been starting this video. Not just this video, all of these videos. They've all taken a long time. I don't think doing these on a day in which I've taught a full day of school is actually a good idea. But at this point, we're sort of committed. I'm sort of past that point where I get to make that choice. Finally, though, I can say that the questions that are on here represent the sort of questions that I actually will ask you on the Essential Skills Quiz in Calculus BC. So I think that's a good enough starting point to run with. So here we go. I'm going to dive into part 4. This will cover the calculator portion of the ESQ. And I want to thank Mr. Nickerson for recommending WabbitEmu back in the day. I did purchase a $170 graphing calculator program from Texas Instruments, and naturally, I'm not allowed to transfer it across two computers because that is a great way to handle educational software. So, thanks, Texas Instrument. Thanks a lot. We're going to begin with question 12a. Question 12a gives you a table of values. So this is our one numerically represented function on the ESQ for the first term of Calculus BC. And then it asks us to find the average value of f on a particular interval. So there's really two things going on here. We have the approximation methods. So the first one's LRAM, second one's RRAM, third one's trapezoid. Those will cycle throughout the weeks, not in any pattern, but they will cycle. But then it's also tacked on in here. I thought this was a smart move on my part. It's also tacked on the request for you to find the average value of the function. So we have to do both things. And then in our table of values here, this is definitely something you'd want a calculator for. You just have 4 awkward expressions for the function values at those points. So again, not a realistic depiction of a function, I would hope. I would hope the square root of 11, e to the pi, and ln of 14 aren't going to show up all the time. But for our purposes, it doesn't matter. We're going to be using whatever the values happen to be. Now, before we get into the approximation method part, sort of the heart of this question, that average value of f on 0 to 13, that entry point is really important. So reading it out of the problem is essential, and then, of course, representing it correctly. So just as a reminder, the average value of a function f of x on the interval from a to b is 1 over b minus a times the integral from a to b of f of x dx. And again, without going too deep into here about the origin story, you can look that up in I think the fundamental theorem lesson was the one we covered it in last year. But basically, this is the expression that calculates for us the average value of a function on the closed interval from a to b. And I guess I do have to say the function has to be integrable, so for what it's worth. So for us in this case, we want to calculate the average value of f on 0 to 13. So regardless of which approximation method we're using, we're going to be approximating the value of the expression 1 over 13 minus 0 times the integral from 0 to 13 of f of t dt. And so we are going to approximate that using LRAM, RRAM, trapezoids, or even MRAM potentially, just not on the ESQ model or likely on the ESQ. So in order to do this, of course, we have to remember that what we're doing is we're adding up a finite number of rectangles areas, and we're going to let those rectangles areas represent the area between the curve and the x-axis that we can't necessarily see based on the limited information we're provided. In this case, what I like to do, though, is I like to go through and actually set up the widths and heights separately. So for instance, as I look at this table of values, I can see that our first rectangle will cover the region from 0 to 4, which means it's going to have a width of 4 minus 0. The second rectangle is going to cover the interval from 4 to 7, which means it's going to have a width of 7 minus 4. And the third interval is going to be from 7 to 13, which means it's going to have a width of 13 minus 7. Now, of course, we know all these values. That's 4, that's 3, and that's 6. But for the sake of construction and sort of instructional purposes, like you can see where those come from. Likewise, there's one other piece here. We also need, of course, the height. That gave us a width. We need the height. The height's going to come from the function value, and this is where that L, R, or M, or even the trapezoid part really stands out. L stands for left. This is asking us to use the left endpoint's heights to determine the height of each of these rectangles we're using for our approximation. So looking on the interval from 0 to 4, the left endpoint would be at x equals 0, which means our height will be f of 0. On the interval from 4 to 7, the left endpoint is at x equals 4, so we'll use f of 4 as our height. And then on the last interval from 7 to 13, we're going to use the left endpoint, which happens to be f of 7. Now, each of those values can come out of the table. So f of 0 is root 11, f of 4 is e to the pi, and f of 7 is going to be the ln of 14. Now, I know there's usually some snarky person out there who just wants to box that as their answer and call it in there, but that's actually not okay on this ESQ. On the actual AP exam, yeah, that would be okay. You could do that. But I want you to round this, or write your answer accurately to the nearest, or to 3 decimals at least. I want to see you doing that computational practice. So I do expect you to go further from here. Also really relevant is that actually what I've written is incorrect. That was an intentional mistake though. Like I'm not gonna overlook it now, but that was an intentional mistake on my part because people often forget that. You get caught up and lost in the actual approximation. We're not approximating the integrals value, which is what we did here, adding up straight rectangle areas. We're approximating the average value, which means we need to multiply this entire thing by 1 over 13. So I'm going to do that on both of these versions. And now I'm going to go to a calculator to make this happen. Now, unfortunately, my calculator is going to cover up some of this stuff. Fortunately for me, I can actually bring this down here and at least give us a little bit of space to work with. So I'm going to dive in here. Here is our Wabbit Emu calculator. So we need to put in this line right here. Sorry, I didn't get that whole thing. We need that entire line right there. So in order to do that, which we can definitely do, I'm going to now just type this in. So we're going to have 1 over 13. And I know there's probably someone out there who's thinking, oh, no, I'll just divide by 13 at the end. I don't recommend that. It's very easy to forget at the very end once you've done a bunch of calculator stuff that you, also I need to divide by 13. Just multiply by 1/13 at the beginning. Far easier. I swear that it's far easier. As far as the other pieces, I'll use my mouse for this. We're going to have 4 square root. Sorry, my eyes aren't great here without my glasses on. We're going to have 4 root 11. We're going to have 3 times e to the pi. Almost said pi I, that's different. And then finally, we'll add to that 6 times the natural log of 14. That's going to give me my average value. My average value is 7.579. 7.579. This is about 7.579. Or if you wanted to, since it has to be accurate to 3 decimals, you could have also not rounded it and just gone with 7.578. The truncated version is correct as well. But for us, I'm going to go with the accurate to 3 decimals. So there is our first one. We used LRAM to approximate our definite integral. Definitely not the hardest thing in the world, but definitely not trivial either. The second one we're going to look at is RRAM. And if I line this up properly, since it's the same region, same table, effectively we're doing the same thing. Just this time we're going to be using the right endpoints. Like just the right endpoints. That's the only adjustment here. So for us, our intervals are going to be exactly the same. I could have stolen them and brought them over from before. So 4 minus 0, we'll have 7 minus 4, and then we'll have 13 minus 7. And by the way, if you're wondering like why I'm not reprising all of that information on the previous one, I figure that if you could figure out LRAM but not RRAM, then all you really need is the next thing. So just know that that's my theory. I guess if you don't know how to do RRAM, and you don't know what to do, go watch the LRAM video and then adjust it so you use the right endpoint. I think that's a fair ask. With all that said, now that we're using the right endpoint, we're going to need to look on each interval and ask what is the right endpoint. So on 0 to 4, the right endpoint is at 4. So this is going to be f of 4. The next interval is from 4 to 7. The right endpoint is going to be 7. So we'll multiply 7 minus 4 times f of 7. And last but not least, on the interval from 7 to 13, the right endpoint's at 13. So we'll multiply by f of 13. Now from here, oh, and once again, look at that, because I copied it over, or because I was copying it over, I almost copied the same mistake from before. We are doing the average value of f on 0 to 13, so we also need to multiply this entire thing by 1/13. Notice I'm putting those big parentheses there. Down below then, as we look, this is going to be equal to 1/13 of, we're going to have 4 times f of 4, and f of 4 is e to the pi. Our next bit is going to be 3 times f of 7, and f of 7 is ln of 14. And then last but not least, we're going to have 6 times f of 13, which is 9.99, almost 10. And from there, we need to figure out the actual numeric value, or the decimal value, so I'm going to ask my graphing calculator to tell me. So in this case, as I mentioned on the previous one, I'm going to multiply by 1 over 13. I do not recommend you wait to do the divided by 13 until the very end. Yeah, it should be the same answer, but will you remember? Like, really, will you remember? I find it easy to miss it myself, so I'm going to recommend you type it first. After that, we'll have 4 times e to the pi. Sorry, it's really hard to see this with my eyes. Then we will have, it looks like 3 ln of 14. Notice I'm closing the parentheses on some of these things. And then finally plus 6 times 9.99. When I press enter, I get 12.3399. So as a heads up, one way you could write that is 12.340. That would be the rounded version of the answer. If you preferred the truncated version, that would be 12.399. And of course, both are accepted as correct in this case. We are looking for your answer to be accurate to at least 3 decimals. Those are both accurate to at least 3 decimals. Finally, we have the trapezoid one, and I will admit the trapezoid one is sort of its own challenge. I'm not going to adjust that, or I'm not going to pretend that it's not. It's just a little more cumbersome. Like, that's the biggest thing. There's nothing else that's super difficult about it. It just takes a little bit more effort to make happen. But we can do this. Having said that, we should probably note what the trapezoid, like what a trapezoid's area is. So just to kind of give you an idea, trapezoids fit this sort of form. It always makes me feel like I'm looking at I think it's like the tip of like those fancy fountain pens that they sell at Staples. I don't know if that's perfect. Looks like something else too, but I can't think off the top of my head. Like a pen knife, maybe? Maybe that's what I'm thinking of, actually. But in this case, it has a couple dimensions. It has a width, it has a height 1, and it has a height 2. Or sometimes you'll see me call this like big height, little height. Doesn't really matter which one we do it. In any event, the area for a trapezoid, which I'm not going to give you the geometric derivation for, but effectively flip it over and then you get a rectangle and you can work from there. At least with this particular one. Otherwise you get a parallelogram. The area of a trapezoid, so it's a trapezoid, is going to be the width over 2 times height 1 plus height 2. So there is our area formula. We have to do that for all 3 trapezoids that we're getting in this particular case. Not trivial for sure. Having said that, we can make this work. So the first thing to note is we've got the width. I'm going to use some colors to make this happen. The widths are going to vary. So obviously we have 3 intervals. We've done them on the previous 2 problems, so they're probably pretty familiar. But our first width will be 4 minus 0, and that will be divided by 2. Our second width will be 7 minus 4. That'll be divided by 2. And just for good measure, our third one will be 13 minus 7, and that will be divided by 2. Each of these then gets its own little, what do you call it, sum of 2 heights, big height and little height, or left height and right height, probably more appropriate to call it that. To figure out what those are, well, we just look at each of the endpoints. So basically, we're going to use every single endpoint in the appropriate spot. So for the first one, we're going to have f of 0 plus f of 4. For our second one, we're going to have f of 4 plus f of 7. And then we're going to have f of 7 plus f of 13. Now we have to go grab all of these values, and I'll totally admit that this is an annoying one to put through on the calculator. Having said that, we can clean this up a little bit. 4 over 2 is 2, and then we'll have some stuff. This will be 3 over 2 times the sum of some stuff. And this will be 6 over 2, which is 3, times some stuff. And again, each of these will be added on the inside. So I'm just trying to clean up as much as I can. We'll just go to the calculator at some point here. Reading out of the table, we're going to get root 11 plus e to the pi. We're going to get e to the pi plus the ln of 14. And we're going to get the ln of 14 plus 9.99. Now, there are ways to combine this all together, but I honestly think that it doesn't make it any better. I think that we've got this sort of as good as we're going to get. Save for one thing, which you might notice for the 3rd time I didn't write out the 1 over 13. Are you noticing how easy it is to forget? I mean, I know the first time I was doing it intentionally. I wasn't doing it intentionally the last 2 times. It just happened. So there's our 1 over 13 to adjust for the average value. So this is 1 over 13 times all of that stuff. Question becomes, what is this approximately equal to? And I don't know. I'm going to ask a wabbity moo. So in here, we've got 1 over 13. And now, oops, I like doing the multiply. No, you don't have to. This is going to be 2 times, looks like root 11. Oops, come on. I totally pressed that button twice. Root 11 plus e to the pi. If you're like, this goes really slowly. Yeah, I know. I put it on YouTube for a reason. Just go speed it up. I assume everyone's watching this on like 2 times speed for the most part, if they're even watching it. I have very low expectations that this one's being watched, which is dumb because this has been 4 nights of my life that I'm never going to get back. But hey, theoretically, I'll never have to do this again. Okay, there's that second part. And finally, we have 3 times the natural log of 14. Yeah, by the way, that came out harsher than I wanted to. Like, I don't hate doing this work. I hate that it's not done. I really, really want it done. Okay, and according to this, our average value here is 9.959. 9.959. And now you might ask yourself if that's a reasonable answer. And to be fair, I'm not 100% sure. It's hard to gauge these things. I'm looking in here, though, as far as different values. I think it's reasonable that this could be in the ballpark because e to the pi is really large. And that's covering a pretty big chunk of space, like that e to the pi shows up. So I think this could be reasonable. It's not ridiculously high, and it's not ridiculously low. So I'm going to go ahead and say that, yeah, why not? Say that it works. What can we do about it anyway? We'll go with that. I have nothing to check this against. I made this up. So there are our 3 approximation problems: LRAM, RRAM, and trapezoids. No MRAM for you. Sorry. Question 13 is our next one, and we're definitely going to have to use WABADIMU for this one. This is all based on derivative analysis, but specifically it's derivative analysis using a graphing calculator. So just keep that in mind. We're using the graphing calculator for the heaviest lifting here. In this case, we've got the function 3 to the sine of x minus e to the cosine x, and we're interested in that function on 0 to 8. So before we do anything else, let's just go ahead and take advantage of knowing this information, and let's get this queued up to sketch on the calculator. So I'm going to put in 3 to the sine of x. We will check in a second, by the way, to make sure that we are in radian mode. Calculus does require us to be in radian mode. And then we'll be in e to the cosine of x for our second term. And now let's do a quick check for mode. It does say radian, so we're in good shape there. And then for our window, I'm going to go from 0 to 8. I want to make sure that I see the correct region. Other than that, I'm not sure what the values will be. So I'm just going to go from -10 to 10, and I'll hit graph. So we can see it going up there for a second. We can see it coming back down again. It's through. It's gone through the x-axis. Then it's going up again. Okay, so there we go. There is our graph. In fact, for this sake, let me go ahead and steal a picture of it, just so we have something we can kind of draw on and look at a little more closely. So not the highest resolution, but that's okay. It does a pretty nice job. So our question here for this particular piece, and I think all of the questions relate to this graph, so in a sense we've just done the heaviest labor. Effectively, we want to now figure out the specifics here. And the first specific that I see asks us, where does f of x have a relative maximum? Well, since these questions also ask us to justify our answer, I might as well do that first. F is going to have a relative or local maximum anywhere where f prime changes from positive to negative. So we're looking for a space where the derivative, which is our graph, by the way, this is f prime of x that we just put onto the graph, where f prime changes from positive to negative. And looking in here, I see that that happens just one time. It happens specifically somewhere in the middle of 0 to 8, so I'm guessing the answer is going to be somewhere near 4. We don't have to guess, though. We have a graphing calculator for that reason. I'm going to go ask the graphing calculator to locate for us the 0. So I'll go over this way. And we'll go over this way. And then press enter. And it says that our 0 is at 3.880. So at x is approximately 3.880. In this case, if you did write 3.88, that is accurate to 3 decimal places, so you're technically okay, but I would prefer that you put 3 decimal places out there. Maybe it's because I like doing this trig star, but whatever the case. So there's our first one. Again, the key element is knowing what that analysis means, and then graphing your calculator and knowing your way around the trace menu, also known as the Widler button. So there we go. For question B, the next one asked us at what x values, or for which x in 0 to 8, does f have a point of inflection? As far as our justification, we'll again do that first. You have a point of inflection when f prime changes. There's more to it than that, don't worry, there's more. When f prime changes, and changes specifically between increasing and decreasing. And I'm sorry, I'm going a little bit stripped down. I'm just sort of feeling the clock tick away on my limited free time, so I'm going to try to abbreviate a few things here. I hope it's still clear. So f prime changing between increasing and decreasing would happen at any local extrema. So there are 2 in this particular case for us to actually go find. So let's find both of them. So once again, go second trace, get into the Widler button. In this case, I'm going to start with the maximum. Now to go find this, I know I'm on the interval from 0 to 8, so rather than like tap, 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 and going kind of wild with that, I'm instead going to start by starting at 1, and then I'll start and have the right bound be 5, and then I'll guess that the thing's 0 at 4. Now, oh, I just put the maximum, jeez. So it did find the maximum, which is kind of wild. That's cool. But I did a weird setup. I think I was trying to bound the 0. We were looking for a maximum here. Fortunately, we found it. So our maximum of f prime is at 1.813. That is one of our 2 points of inflection. So x is approximately 1.813. And let me make sure I read that correctly off there. 1.813. Yeah, and technically it could be 1.8122. And then the other one that we had, there's one more POI. We can see it on the graph. This time I'm not going to do it in a wonky way. This time I'm going to do second trace, get into the Whittler button, and I want a minimum. That minimum, let's go from 4 to 7.9. That lets me skip the tapping, get a little bit closer and press enter. And it says my minimum is at 5.986. And there was no rounding stuff, 5.986. So it turns out that there are 2 places where f prime changed between increasing and decreasing. They were the 2 high and low points that we see up there. That's true. A point of inflection would be a relative maximum or minimum value of the slope. And now that we have them, we can find their values. So those are the places where the POI happens. And if you're like, wait, what about the justification part? Because f prime blanks. Yeah, it's right here. I literally did it right here. I think this is exactly what you write in because I believe I give you the f prime. So just FYI. So leave that on there. What the heck? And then finally, the last one we're going to look at, I think this is kind of a classic question. I feel like these 3 will likely get cycled over the course of the quarter's ESQs. I just feel like they do a nice job of capturing a little bit of everything. So we did extrema, we did POIs. Now we can combine both decreasing and concave up. Although we don't have to. We could, of course, just do one property in itself. But in here, just as I did before, I want to translate this. So first of all, if it says f is decreasing, that's the same thing as saying f prime is negative. And then the second part notes that f is concave up. And if f is concave up, that means f prime is increasing. So we are looking on this graph for the regions or interval or intervals where f prime is negative and increasing. And interestingly enough, I see 2 of them here. I see one region right here, and I see another one right here. Now we have a little advantage as we go in. On the previous problem, we found that the minimum is at 5.986. 5.986. So we already have one value sort of for free, but we do have to find the other ones here. So we have to find the other interval. But having said that, because these are open intervals only, I can start the first one as being from 0 to something. And then from there, the other interval is going to be from 5.986 to something else, to that other 0. So now we need to go find those other pieces. So I'll start with the 0 on the far left. I'm going to go to the Whittler button, second trace, and I'm going to go to 0, 0.5, that'll be on the left of it. And then we'll go up here. You can tell sometimes I like just clicking the button. It gives me some time to think. So it says that first 0 is 0.738. So this will be 0.738. I'll actually go ahead and label it, by the way, right here. 0.738. And now our second one, we've already got the first part. Let's go ahead and do this in pink. We need to find that 0 over on the right side. So we've done some work with that already, but not that specific point. So to find our 0, I'm going to go from 5 to 7.9. The reason I'm choosing 7.9 is I want to get close to 8 without crossing 8, so I'm just going to go 7.9. And it tells us that, oh, I didn't guess the other side. I got to guess. Sorry. I was hoping it was going to tell me the answer. Thank you. It says our 0 is 7.022. So 7.022. You could also have gone with 7.021. But the important thing for us is that we have our interval, and we did justify it right up here. F prime is negative and increasing. So there we go. There is our stuff. So that concludes question 13. Again, it's a lot of calculator work. It's really interrogating the Whittler button up there on second trace. And of course it's... Did you all hear that? I don't like that. It's all dark in my house. Printers don't go off. Why? It's so ridiculous. It takes me 3 minutes when I press print for it to print something, and here in the middle of the darkness, it's just like... I don't understand printers. What I do understand is how to do question 14, and how to finish this thing is me not dallying talking about other things like the creepy spirit-infused printer. So question 14 is the final question on here. In the instructions on the ESQ model, I tell you to use the alternate fundamental theorem. That won't happen on your ESQ. There's no room for it. Instead, it just basically asks you the question. It would just say like 14, and then water enters a small reservoir at a rate given by R of T. Like that would be the process you follow, just FYI. So in this case, there's a couple different variations on this question. That's why there are 3 different problems for it on here. I sort of vary the type that's on there just based on sort of gut feeling. In this first one, we have water entering a reservoir at a rate given by R of T. Who cares what the actual function is? We'll put it in a calculator in a second. And that's for times 0 to 9. It then says 18 gallons were in the tank at T equals 0. How many gallons will be there at T equals 7? So in a sense, what we've got here are a couple different pieces. We have R of T, which is equal to this tangent inverse thing. I'm just going to write it like that for simplicity. I really want to be done. Then we have an amount. We have that A of 0 is equal to 18 gallons, and A of 7 is what we're trying to find. Now, in this case, it's a little harder to tell because we have R there and A here. I've given that name A to be the amount of water in the tank at a given time. But what I'll point out is that R of T is really the rate of change of that amount. So effectively, we have A prime equals this inverse tangent function, and then we have a function value. We're trying to find another function value. That is your recipe for the alternate FTC. If you take a whiff, you can hear that thing cooking beautifully over in the kitchen. So we're going to use the alternate fundamental theorem, no differently than I might use cayenne pepper in something. So as far as the way this is going to work, we're going to set up the fundamental theorem. So I'm just going to use R of T for this. We'll have the integral of R of T dt. That integral is going to run from, and again, just to kind of help you see where it's at. You've done this a lot, so I think you'll get it, but just in case, it's going to run from 0 to 7, and then it's going to be equal to, specifically, A of 7 minus A of 0. Now, in our case, we know A of 0 is 18, so we actually have A of 7 minus 18. To get A of 7 alone, to try to get it so we can solve, I'm going to add 18 to both sides here. When I do, I'm going to get that 18 plus the integral from 0 to 7 of R of T dt is going to be equal to A of 7, the amount that we're looking for. And by the way, it is an amount in gallons, so you might even note right off the bat that this is going to be in gallons, but you don't really have to. It doesn't say include units. As far as its value, though, that's once again a job for Wabbit-Emu. So in Wabbit-Emu, I'm going to go back to the menu. I almost said the menu, like the Wabbit-Emu. Whenever you say Wabbit, it makes me want to say that I have a, what do you call it, a speech impediment. No, I'm not going to tell the speech impediment story. I was diagnosed with a speech impediment when I was in elementary school, but for a bad reason. So we'll come back to it. So in here, what I want to do is I want to put this into my calculator. We'll have 18 plus. Math 9 gets you your integral. We're going to run from 0 to 7, and this will be in terms of x. And then in our function here, our function is, I got to move this over actually. It looks like it is arctangent. So remember, arctangent is tangent inverse, so second tangent. And then it's going to be t squared. Oops, that's t to the minus 1. Go away, nobody wants you. T squared minus 4t plus 1. And at this point, if I close this off, honestly, it definitely took a little while to calculate. This thing isn't as fast as my other model was. This gives us 18.906. So 18.906 gallons. You could have also done 5, so 18.905 gallons. I'm not going to write the other version. I'll just do it that way. So there's our first one. Again, we start with the fundamental theorem. We solve for whatever piece we're missing, and then we just let the calculator do the heavy lifting. You should be doing no anti-differentiation by hand on this question, question 14 on the ESQ, unless possible you're taking the plus ESQ, in which case basically there's no holds bar. Anything goes. The second one we have, I didn't do a motion problem. Usually I would have thought that I would have done a motion problem, but in this case I must have been hungry. We've got a brownies in an easy bake oven. I don't know if you know what an easy bake oven is. You probably do. I feel like that toy's lasted forever. That was a toy that just looked fascinating on TV all the time. That was one of the earliest commercials I can remember. These little kids would make brownies in their easy bake oven, which I swear was just plastic. I don't know how it didn't melt. But in any event, I've never used an easy bake oven. I've just heard rumors about them. Maybe I would have learned how to bake before the pandemic if I had. But in any event, we've got the temperature of brownies in an easy bake oven. Got to be really small brownies. It's probably really cute. given by T prime of T equals that monstrous thing. It's measured in degrees Fahrenheit per minute for times between 0 and 15. It does note here, though, by the way, this is one of those deceptive problems. So it's true for times between 0 and 15, but we are given a temperature at 14 and asked about the temperature at 0. So don't be distracted by this 15 because they're telling us the temperature at 14. An easy thing to miss, and I totally would understand why. This is an inconsiderate question, but the world is full of inconsiderate people, so why can't a few questions be rude as well? With all this said, knowing where we're at here and thinking about the fact that we're given a derivative, we're given an amount, and we want to find another amount, this screams for the alternate fundamental theorem. And in fact, I think it's almost automatic setting this thing up. This will be the integral of t prime of t dt. It's a lot of t. It hasn't been this much t since Boston's Harbor. Talk about a throwback. This will then be equal to what we can call capital T of something minus capital T of something. Now, you might have caught me there for a second, almost automatically going t of 14 minus t of 0. But I'm going to let you in on a little secret. If I'm doing this problem, and to be fair, I'm pretty darn good at this problem, this might be one that I don't know that I ever miss. Like, it's kind of wild to think about, but I'm not sure I ever missed this. One of the reasons why is that I minimized the computation and I minimized the algebra in this problem. So this problem is easy if you just add this particular piece over to the other side. That way there's just one move to kind of get everything into position. Well, the problem is if we put things in chronological order here, we would go from 0 to 14, which would mean we know t of 14 and we're trying to find t of 0. So we would have to solve for this, which involves moving something and then twisting something around. I don't recommend, we'd be solving for this, which involves a whole bunch of moving. I'm not going to do that though. I have a much faster way to do this. I'm going to write my integral as ranging from 14 to 0. When I do that, it reverses the limits of integration, which then makes this t of 0 minus t of 14. The advantage in doing it this way is that, yeah, we don't know what t of 0 is, but we do know t of 14 is 94.5. And since 94.5 is our piece and we're trying to solve for t of 0, all we have to do from here is add that 94.5 to both sides. As soon as we do, we get 94.5 plus the integral from 14 to 0 of t prime of t dt is going to be equal to t of 0, the initial temperature, and of course our calculator can find this. So pulling over here, if we punch this in, 94.5 plus Math 9, be real careful to put this in correctly, 14 to 0. In here we'll have our function, which is miserably long. Thanks a lot, person who wrote this ESQ model. What the heck were you thinking? What a jerk. You're the derivative of the acceleration function, person who wrote this, who definitely isn't talking to the screen right now all by himself while his day mercilessly continues forward. So there's our function, and then we're going to do this in terms of x. So in doing it this way, it's going to eventually give us an answer. It's pretty slow. I've given you a crunchy function. It says that this thing is going to have a temperature of 26.530. So 26.530, which means that the brownies were frozen. Oh, you know what? That makes sense. It's the initial temperature. It's totally possible for the brownies to have been frozen, maybe. I don't know how people put together the stuff to put in an easy bake oven, but that makes total sense. That absolutely could have been that they were put into the freezer for a while before going into the easy bake oven. Now, having said that, the fact that they went to 94.5 degrees means that it gets pretty hot, which is dangerous for a little kid, and that is who the easy bake oven's made for. But having said all that, that does make sense. Now, with that said, though, if something bothers you about switching these limits of integration in this way, let me just prove to you that your concerns are ill-founded. I'm going to do this over here, and I'm going to do it in orange just so we have it separate. Instead of doing it in this order, I'm going to put it in the more traditional order here. Let's go with some Kasumis Oak stuff. We're going to shoehorn this. We'll go from 0 to 14. This will be t of 14 minus t of 0. We know t of 14 is 94.5. And so now I need to solve for t of 0. So I'm going to add t of 0 to the left side and subtract the integral. That will give me t of 0 equals 94.5 minus the integral from 0 to 14 of t prime of t dt. Now when you look at this, and you look at this, like, yeah, there's similar ingredients, but they certainly are not the same thing, right? They're just written differently, but they are the same thing. These are the exact same answer. And in fact, I'll prove it to you. Second entry. I'm going to copy that entry again. I don't want to retype this whole thing. In this case, once we get in there, we're going to have 94.5 minus, and this time it will go from 0 to 14. And of course, the function's the same. It's going to come out to be the exact same value. So basically, as soon as it's there it is, the exact same value. And as you look at this, your mind might go, yeah, but that doesn't make sense. It's different. Like, there's a minus sign there. But in reality, other than the fact that, like, yeah, of course it's the same. These are the same thing. We've just approached them slightly different ways. In reality, the property that's happening underneath this, just so it's clear, is this one. That the integral from a to b of f of x dx is the same thing as the negative integral from b to a of f of x dx. In a sense, what we've done is we've reversed the limits of integration from over here, where it was plus the integral from 14 to 0. That introduces a negative sign, and that's it. Like, they are exactly the same thing, which is kind of cool. Even cooler is that I'm near the very end of this. Even cooler than the fact that I'm on to my last problem after this week-long project that I didn't even have planned and has eaten up something like 6 hours of my time. Even cooler than that are the brownies before they went into the Easy Bake Oven. The last question we got is sort of a anticlimax. It's an anticlimax because it's the most bare bones boring one. This is the question where I've sort of given up when I'm writing the ESQs. I tend to rewrite most of the ESQs fresh each year. And if you see one like this is me just going, yeah, I've got nothing for you anymore. I've got nothing left. And hey, what a perfect time. What a perfect feeling to capture how I feel right now. I've got nothing left. I want this done. I want to get this banana suit off. Although I've got that healthy yellow glow going here, so that's kind of cool. I'm shiny. Or, no, that's like the crab from Moana. I'm missing my point. Let's do it. So first of all, does this match the alternate fundamental theorem setup? Like, do we have the right ingredients to follow the recipe? We have a derivative, we have a function value, and we want a function value. That's exactly what we're looking for. So let's do this. We're going to do the integral of g prime of x dx. That's going to be equal to g of something minus g of something. Now let's take advantage of what we learned on the previous problem. Oh no, I didn't do the previous problem. Then go back, just go do it now. Like, I explain it much more in depth what I'm about to do, but your call, like, whatever, I'll do it here. So what I'm going to do is I want to make this as easy to evaluate as possible, and of course take advantage of the graphing calculator. So what I'm going to do is, since I know it's easier to add this over than to solve for it, what I'm going to do is I'm going to reverse my limits of integration again. I'm going to write my integral not from 1 to 4, but from 4 to 1. What that will do is it'll make the right side g of 1 minus g of 4. And now since g of 4 is equal to 11, actually I'm just going to go ahead and copy this. I am so done. I'm going to go ahead and do it. I never do this. I'm doing it. I'm doing it, folks. I'm doing it. G of 4 is 11. So now all I have to do is add 11 to both sides. So plus 11. Where is this going to leave us? It's going to leave us with 11 plus the integral from 4 to 1. Don't worry about them being out of order. It takes care of itself in the calculator. This is going to be equal to g of 1. And now the question is, I don't know why did I go over there. The question is then, what is this equal to? And you know what? We're going to let Wabbit Emu take it home. Wabbit Emu? Let's do it. 11 plus math 9. We're going to go from 4 to 1. Again, you don't have to add a negative sign or anything. Just keep it faithful, exactly what's written. And then in our function, I'm going to put in this square root of, it looks like 2 to the cosine of x plus 7. Make sure that 7 is down, not in the exponent. It's an easy mistake to make. I've made it before. And then finally, this will be in terms of x. 2.659. So it's telling us that g of 1 is approximately 2.659. Let me check one more time because I don't want to ever redo this again. 659, there it is. So there is the approximate value of g of 1. So, I'm just realizing you could ask this question as, like, what is the average rate of change? That's kind of cool. Beside the point. In any event, also beside the point is any more problems here. If you're like, wait, but there's one more. Oh, you can't see it at the bottom. As I say, at the bottom it says 48 out of 49. There's nothing on the last page because I'm done, folks. I am done with this. Obviously, I still have to render it. I still have to convert it. I still have to convert the video solution links and then upload it so I can add the links. But I've done all the work of the writing or the video portion. I am so thankful to be done with this. Gee, who can I thank? I can thank all the Major League Baseball playoff games I haven't watched because I've been doing this. I can thank the ridiculous headache I have because of this. I can thank all the sleep that I've forfeited to do a couple extra hours of this. Yeah. Yeah. Don't overpromise stuff. Should all learn not to, I don't know, not to set high expectations for yourself. That's terrible. I'm just going to stop now. So yeah, I've finished it all. I've done all 47. No, I don't think it's 47. I think it's 44 because I've had all those little menu items. Maybe it's 43. Probably it's 42. That'd be appropriate for me. More appropriate for me is that I'm done. Thanks for watching if you have. And yeah, there's your stuff. I'm going to post this as the written solution so that you have access to them. I'm not handwriting these again. My wrist is killing me from all this. So yeah, thanks for watching. Have a good night. Or morning, I guess. That's fine too. Have a good one.